All right, today we're going to unpack one of the most important, most influential papers in the history of modern AI. It's called Deep Residual Learning for Image Recognition. And believe me, it didn't just move the goalposts, it completely changed the entire game. So back around 2015, the whole AI world had kind of hit a wall. Everyone knew that making neural networks deeper, just adding more and more layers, should make them smarter. But for some reason, it was actually making them worse. And then this one paper came along, introduced the world to what we now call ResNets, and solved this massive mystery with an idea that was honestly surprisingly simple. And this quote from the authors really just nails the problem perfectly. Everybody in the field knew that deeper networks should be way more powerful, but trying to actually get them to work, it was a total nightmare. And get this, to prove their new idea really worked, the authors didn't just train a deep network. They trained a network with an absolutely mind-boggling 152 layers. I mean, that's like 8 times deeper than what was considered state-of-the-art back then. And the results? They were just staggering. Okay, so let's really dive into this paradox, because it was a real head-scratcher that was baffling the entire AI community. Logically, you'd think that if you just keep adding more layers to a neural network, giving it more power, more complexity, it should always get better, right? Or at the very least, it shouldn't get any worse. But yeah, that's not what was happening at all. Researchers kept finding this really weird thing. You can actually see it right here in a chart from the paper. A 56-layer network was consistently performing worse than a much shallower 20-layer network. It's like adding more brainpower was somehow making the network dumber, not smarter. It made no sense. Now, the first thing everyone probably thought was, oh, it's just overfitting. That's a super common problem where a model gets too good at memorizing the training data and then fails on new stuff. But that wasn't it. The real problem was something much, much weirder. It was this thing they called the degradation problem. And here's the crazy part. The super deep models were failing on the very same data they were trained on. That means the network itself was fundamentally broken, struggling to even learn in the first place. It wasn't about seeing new things. It was a core problem with its ability to optimize. So, how in the world did they fix this? Well, the solution wasn't some ridiculously complex new algorithm. Nope. It was just an incredibly elegant, simple shift in thinking. They came up with this idea called residual learning, and it's brilliant. Instead of forcing a network layer to figure out the entire perfect answer from scratch, they just asked it to learn the difference, the residual, between the input it received and the answer it was supposed to give. Think about it like this. The old way was like telling an artist, here's a blank canvas, go paint the Mona Lisa. That's a really hard thing to do from nothing. The new way, residual learning, is totally different. It's like giving that same artist a pretty decent sketch of the Mona Lisa and just saying, hey, can you touch this up? Just make the corrections needed to make it perfect. See? It's a much easier, more focused job. And just like the author suspected, it turns out it's way easier for a deep network to learn a bunch of tiny little changes than it is to learn a whole complicated function from absolute zero. So how did they actually build this cool idea into a network? Well, the answer is a simple but totally brilliant architectural trick called a shortcut connection. Here's how it works. They created these shortcut connections where the original input signal literally just skips over a couple of layers. It takes a bypass route. Then, at the end of that block, it gets added back to whatever those layers came up with. This simple little trick forces those layers in the middle to focus only on learning that small residual change, because the main information is already guaranteed to get through. It's so clever. So, with that degradation problem finally solved, the floodgates just opened. There was nothing holding them back anymore. Researchers could suddenly build networks that were deeper than anyone ever thought possible, and the crazy part was they just kept getting better and better. And the results came in fast. A 34-layer ResNet, as they called it, easily crushed a normal 34-layer network. Right away, they knew they were onto something huge. But of course, they didn't stop at 34. They just kept going, pushing it to 50 layers, then 101 layers. And with every jump in depth, the network just got more and more accurate. The degradation problem was officially a thing of the past. Eventually, they pushed it all the way to that magic number,
152 layers. They had created the deepest, most powerful image recognition network the world had ever seen at that point.
And this wasn't just some academic exercise. The ResNet models entered the huge 2015 ImageNet competition and achieved an error rate of just 3.57%. I mean, look at that. They didn't just beat the previous winners, they absolutely crushed them.
And it wasn't just that one event. That year, ResNets became the foundation for winning first place across 5 different major computer vision competitions. They didn't just win, they completely dominated the entire field.
But the impact of this paper, it goes so much further than just winning a bunch of trophies in 2015. It really laid a whole new foundation for pretty much all of modern AI. See that little residual block with its shortcut connection? It basically became a fundamental Lego brick for building AI. It's now a core, essential part of the massive neural networks that power everything you use today, from the large language models that run ChatGPT to the AI that generates images in Midjourney. It's everywhere. You know, the story of ResNet is just such a perfect reminder that sometimes the biggest breakthroughs don't come from more complexity, but from questioning our most basic assumptions. It really makes you wonder, doesn't it? What other obvious ideas about AI are we all just accepting as true today that might just be waiting for another beautifully simple shift in thinking to come along and change everything?